Good afternoon, everyone. I will be talking to you today about an R package I developed called Matter for working with larger-than-memory datasets on disk in R. I'll start off with a motivating example of where I'm coming from in my own work that required me to develop this package. I'll give you a description of my package called Matter, and then I'll give you some examples and comparisons with other similar packages that already exist for similar problems. So as a bit of background, I am also the developer and maintainer of the R package Cardinal for statistical analysis of mass spectrometry imaging experiments. It's hosted on Bioconductor, and so this was my first R package. It has seen quite a bit of use, which I'm quite happy about. But so most of the data sets that I work with are mass spectrometry imaging experiments, so they look kind of like this. A lot of my data are hundreds of thousands of mass spectra from hundreds of thousands of different pixels in an image. And so this is kind of where I'm coming from in terms of data sets. It's large, high-dimensional imaging data sets. But recently I've been running into a problem in terms of working with recent mass spectrometry imaging data sets in Cardinal, and that problem is that these files are growing much larger and larger as the technology advances. With mass spectrometry imaging, we're continually seeing increasing spatial resolutions, increasing mass resolutions, producing larger file sizes, and as these experiments grow more complex, more scientists are starting to use larger sample sizes, more complex experiments, all of this making it much more difficult to actually work with the data files in R. Because when I first wrote Cardinal, I did the typical assumption that many of us make when we start working with data in R, which is that all of the data would be loaded into memory and that I could work with data as an ordinary R matrix or data frame or so forth. And very quickly that became no longer the case. As you can see, I have a lot of comments from my Google Help group that lots of people are working with very large data sets using Cardinal that it was not working. So just to give an example of the specific kinds of files that I work with mass spec imaging, I really wanted to be able to work with the existing file formats that were out there, especially because some of them are open source and were developed specifically for interchange of mass spectrometry imaging data sets in an open source way. So the most popular out there is called IMZML, which is a combination of XML metadata along with a binary data file. And there are two forms of IMZML. There's the processed here on the left and the continuous IMZML format on the right. And both of these start off with a universal unique identifier at the beginning of the binary file. And then depending on whether it's in this continuous or processed format, you have the MZ values and then arrays of the intensities for the mass spectra. And both of these file formats are not actually out-of-the-box compatible with big memory or FF. I would have to convert them to get them into a format compatible with those packages. And also note that because this is an open source format, most of the instruments don't actually natively export to this format. Most of the file formats produced by the instruments are already in some kind of proprietary format, and they have to be converted to this IMZML file format already. So a problem that I would run into is it would be difficult for me to talk to biologists or chemists, and after already asking them to convert their files to this open source format, asking them again, or having to do myself again, converting the files again to some other format that could be used with big memory or FF or some other file format such as netcdf or HDF5. So it was really important to me and to other people in my group that we would be able to work with these files as close as we could, at least to the original data set. And for us, that meant working with this open source IMZML format. It really improved. We believe that doing this would result in more reproducible research without having a bunch of files proliferate across our hard drives. Also note that each of these files are typically one sample per file, and each of these files for higher resolution experiments can grow to be anywhere from a gigabyte to several hundred gigabytes. So with an experiment with multiple files, we would want to be able to address multiple files as part of a single data set. So the solution that I came up with is to develop this R package Matter for working with large data sets on disk. And the idea behind Matter is really to emphasize flexibility in terms of what kind of files and what kind of data sets it can work with. It's adaptable to essentially any kind of open source file format. And it's based on this idea of building a data set from smaller atoms. And I'm going to talk a little bit more about what that means in just another slide or two. So it's designed for statistical method development. So when you have some sort of new file come at you from an experimental lab and you want to work with that file, hopefully you would be able to use Matter to work with that file as quickly as possible rather than trying to convert it to another format or spend a lot of time and headache trying to figure out how to read it into R. It has efficient calculation of summary statistics and all of your other apply type methods that you would expect in an R package are also available and implemented in Matter. So what exactly is the data representation that I'm talking about in terms of this being flexible to many file formats? So Matter is based on this idea of atoms, where atoms are an S4 class in this package. And an atom, what I'm referring to an atom is a sequence of data elements stored in a contiguous location on disk. And an atom also has this property that can be loaded into memory in a single disk read operation. And so each atom is defined by a path to a file containing the data, a byte offset from the beginning of the file, and an extent giving the number of data elements for that particular atom. And the idea is basically that that any kind of data set can be described as a combination of atoms. And so I have two primary classes. Atoms, which describe these atoms, and then the Matter classes, which are the user-facing data structures, are essentially just these atoms with additional slots or attributes, such as length, dim, and so forth. So what does this actually look like? So if I were to load Matter in R, and I created a new vector, by default, if I do this without specifying an existing file or anything like that, it'll create a temporary file. In this case, I'm creating a length 10 vector with integers from 1 to 10, so it'll create a temporary file. And in this very simple case, that results in just one atom with a single file, and then that atom corresponds to that whole file. Now I can create a second vector called y. This will create a second file. And now here's the cool part, which is that we can just combine these together like you would any vectors in R. And what results is a vector that has the combination of x and y, but it doesn't change any files or anything like that. So now this new vector z just has these two same atoms which refer to these two same files, and I can just transparently address those files as two files as a single vector from R. And we can go further than that. We can say combine that vector z with the original x and y to create a matrix. And so here in this case, I have a matrix A that has the combination of all of these, that has 4 atoms, which are all just referring to these original 2 files in this particular configuration. Again, absolutely nothing has changed on disk. This is all just the metadata in R that describes this particular configuration of files and how that maps to the representation that you get in R. And again, an atom doesn't actually have to refer to a whole file. It can refer to just parts of a file. So here, I'm fully specifying exactly what each atom is in this particular matrix. So in this case, I'm specifying that the first atom, which is the first row, corresponds to the second half of that first file, and the second atom, which is the second row, corresponds to the second half of that file. And I'm just doing that by giving this, specifying this byte offset with 5 elements times the size of an integer. So you can use basically this technique to build up a potentially really complex data structure from different parts of a file, different parts of files, and so forth. And the idea here is that we want to be able to address multiple files, multiple different parts of those files as a single data set in R, and just be able to treat it like an ordinary R matrix. So in terms of features and the types of data representations we have available, currently in the version that's currently on the release of Bioconductor, we just have vectors and matrices. But in the development version that's on GitHub and will be in the next release of Bioconductor in the fall, I've also implemented ND arrays, lists, character vectors. I think this is the first package that has support for on-disk character vectors. I'm not sure, but I've never seen any others. And data frames. Another cool thing that we've done is have support for delayed operations. So with many other packages like Big Memory or FF, if you want to do some kind of addition or subtraction or comparison and get an object out of that corresponding to that addition, all of that is actually executed when you do that, and then you have to save the result as some sort of large object. With Matter, I implemented these delayed operations so that all of that is delayed until you actually access the data. So if I had those matrices, if I had this matrix A and I wanted to add it to itself, that wouldn't actually change any data on disk, and it wouldn't actually create any new data beyond the simple metadata that at some point, whenever I access the result of that, it'll add those values together on the fly. So some examples and comparisons. So the primary other packages that are used for this kind of thing are Big Memory and FF. Big Memory is just homogeneous 2D matrices. It uses shared memory for in-memory matrices, and it uses the system call mmap for file-back matrices on Unix-type systems and the Windows equivalent on Windows. The file-back matrices are flat files, so basically just starting with the first data element and then going a sequence straight all through to the last data element. I'll note that since Big Memory uses its own memory management, it doesn't allocate memory using the standard R methods of allocating memory. It was difficult to track exactly how much memory Big Memory was using. I couldn't actually find a way to do that from R, so if anyone has any suggestions on that, please let me know afterward. FF has support for vectors, matrices, arrays, data frames. It also uses flat files for objects. Its data frames can be a little bit more complex. Its data frames can exist from different files. You can create functionality similar to what I'm doing with Matter and FF by using virtual windows, but I found that to be kind of clunky and not totally intuitive. Also, despite documentation suggesting otherwise, I personally experienced a limit of 2 to the 31st total data elements when I was trying to use FF. That seems contrary to what documentation would suggest, so if anyone has any workarounds or solutions for that, maybe I'm missing something, again, please let me know. So in this first example is just linear regression on a 1.2 gigabyte simulated data set. You can see that in general, Matter used much less memory than either Big Memory or FF. It was slower than Big Memory and faster than FF in this example. I'm going to move kind of quickly through these since I'm low on time. In this principal components analysis, again, Matter used less memory than Big Memory or FF. It was slower than Big Memory, but faster than FF. And here I'm going to show some examples on real data, these mass spectrometry imaging data sets from an open source repository cited on the left side. So this is the smallest data set in this particular repository, 2.8 gigabytes. It took 13 minutes to fit the first 2 PC using Matter. But what was surprising with these real data sets is actually the larger the data sets become, the better our performance was compared to Big Memory. So on those smaller data sets, Big Memory was faster because it could load all of the data into memory, which it would do using that mmap call. Whereas with Matter, we're expecting the data set to be larger than memory, so we're only loading what we need very efficiently. So we actually end up faster than Big Memory for the largest of these data sets. We tested up to 42 gigabytes these data sets. So in summary, in addition, I should mention that I had to convert all of those data sets, of course, to big memory and FF compatible format. So that took a significant amount of time. Matter typically used less memory. It was faster than FF, sometimes slower than big memory, but became faster than big memory for much larger data sets. Thank you for everyone. So Matter, it's available on Bioconductor and also on GitHub. Thank you.
Questions? We have our first question.
Thank you. Fascinating work. I wanted to ask if you intend to add support for dplyr verbs for your work.
Eventually, that would be something very nice to add. It's not on my highest. So the question was whether I intend to add dplyr-like functionality. Down the road, that would be something I would really like to have. It's not on the highest on my priority list right now, since I want to add more functionality before that, just in terms of like arithmetic and more delayed operations, like so I can add things together and things like that. But I would like to have that at some point, yes.
So I was wondering, you probably said that, but if you have large data that you combine but do not summarize, but instead want to write out to a new matter, what would be, is there a way to do this, and just how? Yes.
So you have large data that you want to summarize, but...
No, I don't summarize yet.
Oh, you don't want to summarize.
But I want to write it back to disk in a different matter.
Storage. Oh yeah, so that's another thing that you can do with Matter is basically you can use it to define your own file format or file structure and write things to disk however you like, essentially. Yeah, you just create a Matter object and then assign into it, basically.
Any final questions? All right, awesome. Thank you, Kylie.
Thank you.